Alright, our third video, we have the objective of using algebraic tests to find symmetry of a graph and use that symmetry to help us in graphing the actual equation. Okay, symmetry is when a graph can be split into two parts and one half is a mirror image of the other. The presence of symmetry can help you for graphing because you only really need to find one half of the graph and then you can mirror it to the other side. So if you happen to be point plotting, you can just find half of it and then mirror it to the other side. Now in our last video, when we made the parabola, if you remember when we had to add a couple more points, well, we didn't have the whole picture of that graph, but we did use the fact that the parabola was symmetrical to graph the rest of the left-hand side of it. So we did this a little earlier. Now we're just going to do it a little more formally. So first understand that there's three different types of symmetry. You could have a graph that is symmetric about the y-axis. Here's an example. Okay, if you take a look at that parabola right there, it's a mirror image across the y-axis. So that's an example of something that is symmetric about the y-axis. Okay, you could have symmetry about the x-axis. Something like this. Okay, it's a mirror image across the x-axis. And the third type of symmetry that you can have is a graph that's symmetric about the origin. Like this. Okay, it's a mirror image across the origin. And I hope you guys can see that. But if I take this point right there, it gets reflected straight across to right there. Okay, if I take this point here, that is also reflected through the origin to there, even though I didn't draw it through the origin. That is what is meant by symmetry about the origin. Alright, so we have algebraic tests. In other words, without looking at the graph, there are ways that we can see if a graph is symmetric using just algebra. Those three examples that I showed you, you looked at the graph and you recognized that there is symmetry. Okay, now we're going to use algebraic methods to determine. Now they're a little bit tedious, but eventually we learn some little shortcuts that help us along the way. And if you're one of those that kind of sees a shortcut, then bring it up in class and point it out to us because it's helpful. I'm not going to talk about it on here, but if you happen to notice it, let us know in class. Alright, in order to find if it's symmetric about the y-axis, you replace all of the x's with a negative x, and then you simplify. If the function is equivalent to the original, then it is symmetric about the y-axis. Okay? It seems more difficult than it actually is. This is what you do. Suppose we have x squared plus 3. You replace all of the x's with a negative x. And it looks like that. Okay, and then you simplify what you have. A negative x squared is just x squared. Which means that the equation that we end up with looks exactly like the one that we started with. Okay, that means it is symmetric about the y-axis. On the other hand, if you have an equation that looks like this, and you replace x with a negative x, you end up with this formula. And when you simplify it, that negative x squares, making it positive, but a 2 times a negative x becomes a negative 2x. So the equation that we end up with is not the same as what we started with, so that equation is not symmetric. Okay? So replace x with a negative x, whittle the equation down, and see if it's the same as it started. Okay, yeah, so in the last example, the first one was symmetrical about the y-axis. The second one was not, and then if we take the actual look at the graphs, you can see that the one on the left-hand side is definitely symmetric about the y-axis because it's a mirror image this way and this way. This one over here, this point here is not seen over there. So it's a little bit off-center, so it's not symmetric about the y-axis. Alright, the test for symmetry about the x-axis. Replace all the y's with a negative y. And once again, if the resulting equation is equivalent to the original, then it is symmetric about the y-axis. I'm sorry, then it's symmetric about the x-axis. Alright, so let's take a look at this example. X squared minus y squared equals 1. Alright, so if I take that equation, I replace the y with a negative y, it looks like this, and when I simplify it, it looks like x minus y squared equals 1, which is the same as the original. So that means it's symmetric about the y-axis. That means it's symmetric about the x-axis. Okay? And the graph ends up looking like this. So clearly that one is symmetric about the x-axis. Now the last type of symmetry we have to test for is symmetric about the origin. The test is a little bit different because we don't just replace one of the variables, we replace I need a drink. Refreshing Coca-Cola. Unfortunately for me, Danielle is not here to share it with. Now maybe I can speak. Okay, so rather than replace just an x or just a y, we replace both the x's and the y's with a negative x and a negative y. And again, you look to see if the equation is equivalent to the original. So, let's try the example on the left first. If I replace an x with a negative x and a y with a negative y, it looks like this. If I simplify it, it looks like this. Now, I generally do not like to leave an equation with a negative y equals. So if you notice, I took this first equation and changed the sign on everything. So the negative y becomes positive, positive x becomes x squared becomes negative x squared, and so on. Now, how does that equation compare to the original? It's different. Therefore, that particular equation is not symmetric about the origin. This example over here, replace x with negative x, y with negative y, we get this. We simplify, and we have negative y equals negative x to the third plus 3x. Well, again, I don't want that negative y on that side, so I change the signs for all of them, and lo and behold, the original is the same as the equation that we got. So that one happens to be symmetric about the origin. What does that look like graphically? Okay, the first one is a parabola. We already had this graph earlier, right there. The second one is a cubic function, and it looks like what we have right there. So if you can't see the symmetry, allow me to help. This point right here is right there. It's reflected across the origin. This point right here is reflected across the origin. Okay, so that's what's meant by symmetry about the origin. Okay, and that's it for this video.